Let's take a look at the scene first. We have our spatial node. Then comes the camera looking down on everything. And then right in the center an ellipsoid. And within this ellipsoid we have a yellow sphere. Now we want this yellow sphere to orbit in any elliptic form we desire it to. And in particular this example, we want the form of the orbit to be similar to the form of the ellipsoid here, sort of simulating a gravitational pull the ellipsoid has onto the sphere in this x and z plane. And since the camera is above everything, we can give it a try. As you'll see, the sphere will crash into the ellipsoid. That's because I set it up to start at the center. Now if we try again, you see it works fine. Now inside the code you can see I have extended the script towards the spatial node, not towards the sphere, but I've grabbed the sphere here on line 10. Then we have here a bunch of necessary variables initiated, and here the orbit function, which does the actual translation onto the sphere that we have grabbed here in line 10. Now going inside the orbit function, let's first ignore these 4 lines and start at line 17. And here you can see we have redefined x to be equal to 2 times sine of a and z to be equals to 4 times cosine of a. And why so we will see in the next graphic. Alright, just like in Godot, we have here our z-axis and our x-axis. And we want our yellow sphere to have an elliptic orbit represented by this ellipse here. Now any point P on this ellipse or on this elliptic orbit has the following coordinates: zx from z from the z-axis, x from the x-axis. And since P lies on an ellipse, we can represent the point also the following way as a times cosine of t, comma b times sine of t, where t goes through all the numbers we want it to go. Now what is a and b? A is simply the distance the ellipse or the orbit has towards the z-axis, and b is the distance the ellipse has towards the x-axis. Now applying this to our example in Godot, which is here a top-down view of our example, we have here the yellow orb again and the ellipsoid. We can see that the ellipsoid has here a distance of 1, meaning it goes 1 square up on the x-axis, and here it has a distance of 2, meaning it goes 2 squares to the right on the z-axis. Now again, our yellow sphere needs to have an orbit like this, not touching the ellipsoid. Since we can't touch the ellipsoid, or we don't want to touch the ellipsoid, that means we have to choose our b at bigger than 1. So bigger than the distance the ellipsoid crosses on the x-axis. And we have simply chosen this twice to be twice the distance, making it 2. And the same for our a here. We have chosen it twice to be the a on the ellipsoid, making it 4. So again, if I make this one again, then here is now our a equal to 4, and here is now our b equal to 2. And looking back at our code, we can see that that's what we have here. So what we have so far is we have a set of vectors corresponding, we have a set of vectors that push our sphere, here's our sphere from the origin, that's the origin, onto a point on the ellipse. So again, here's the sphere at the origin, we have a vector here that's pushing it exactly onto a point of the ellipse. Now let's take a look at the variables again. We have here a t and b, which are of importance, and we can find them down here, and we can see that b is actually just a constant, 0.5 times pi times delta, and t is a summation of b. So as the frame rate, as the script executes, t increases by 1b per frame. Now that we know what t does, we can start with the first frame. There we get our first t. We input, or we call our first t1. We input it into orbit function, this t1, and look at our orbit function now. We ignore again the first 4 lines and input for these two a's t1. Then we get a vector generated by t1, and then our sphere is translated by this vector onto a point of the ellipse. So here again, here's the vector generated by t1, and then our ball from the origin is translated to the point on the sphere. Now we generate a t2. Continuing this function, we get a t2, we increase t again by 1b, and we get a t2. We input this t2 into our orbit function. Now we look back into our orbit function again. And now we have to be careful. So if we ignore these 4 lines here, what will happen is, if we were to ignore them, we would generate a vector with this t2 we have now, and we would translate our sphere by this vector. But since our sphere is not in the origin, if we were just to simply apply, it's on a point on the ellipse now, it's not back at the origin. If we were simply to apply this vector onto our sphere would exit the orbit. So what we need to do is, and which is exactly what these 4 lines are here for, so we need to reverse the movement by this vector t1 gave us. So again, first we had a t1 gave us a vector, we moved our sphere by this vector. Now we move our sphere back onto the origin. We have a t2 gives us a vector, and now we move our sphere on by t2 onto a point of the orbit, or onto a point of the ellipse. So it's not actually a fluent orbit, but it's sort of, you can see it as a zigzag or something, where you first move by t1, then you get a t2, then you move back by t1, then you move by the vector generated by t2, then you get a t3, then you move back by t2, then you move by t3, then you get a t4, and you move back by t3, and then you move 4 by t4, and so on and so on. So to sum up the basics again, we generate t1, we put t1 into our orbit function, we generate a vector using t1, we translate the sphere via the vector generated by t1, we generate t2, we put t2 in our orbit function, we undo the operation by this vector that was generated by t1, we generate a vector with t2, and we translate the sphere by the vector generated by t2. And that's basically it. I hope it was helpful.